Okay, so let's start. So just to remember where we are, we're talking about learning or representing probability distributions, learning probability distributions, and doing inference with probability distributions. So last time we talked about representations a little bit and derived inference algorithms, or talked about inference algorithms. So basically, given a BaseNet, and this is a special case of BaseNet here, that is a tree, you should be able to, given a query, like what's the probability of U being 1 and S being 0, given that you have a representation of this tree, you should be able to compute it. And what does it mean, a representation of this tree? It means that you have all the conditional probability tables, which we represent this way. So in this specific way, you have one node here that has no parents, P of y, and all the other nodes have parents. In fact, because it's a tree, all the other nodes have a single parent. So you have a small size conditional probability tables here, and you can compute any, and given these numbers here, and the fact that the join can be written this way, you can compute any probability that you want given this distribution. That's clear? Questions? Okay. So what we want to do today is we want to learn these probability distributions. And the question is, first of all, what is exactly the learning problem? So given data, assumed to be sampled from a tree-dependent distribution, and you have to think a little bit about what does it mean that the data is assumed to be sampled from a tree-dependent distribution. It goes back to when we talked about generative models. So really you assume that the data is generated from this kind of distribution. So in order to generate this n plus 1 tuple, you actually started by generating y according to P of y. Given y, you generate a w, given the probability P of w, given y, and so on. So that's what you should have in mind. Then we want to find, given this data, find the tree representation of the distribution. And again, you have to think about what does it mean finding the tree representation of the distribution. And really, this is actually not phrased so well, because there's no notion of D. I mean, it could be that depending on the data that you see, there are multiple trees that you may be happy with. The only question that we want to ask is, what does it mean that we want to find the tree representation? And the only tool we have is really maximum likelihood here, right? So we're going to find the most likely one given the data, which means we're going to compute the probability of the tree given the data, use Bayes' rule. And once we have this, we're going to try to maximize it. So the tree that we're going to find is going to be the one that maximizes the probability of the data given the tree. And I'm writing it this way. So this is a product over all data points, probability of the tree of the data that I observe. Probability of the data based on the tree model that I'm currently entertaining. So, and of course, this explains why we need to do inference and why we need to do this specific inference given that I want to learn the problem. So I talked last time about two inference problems with BaseNet or with representation in general. One of them is computing the probability of an event, and the second one is finding the most likely explanation, sort of argmax over assignments, find the most likely assignment. So here we care about the probability of computing an event. Okay, so I'm just spelling this out. Again, I have one product that is due to the independence of the data samples that we have, and the second one that is due to the tree assumption, right? So the assumption that the representation of the tree reflects some independence assumption, and these are the independent assumptions. The probability of this data point given the tree is the product that I write here, with a slight abuse of notation that if it so happens that a node has no parents, I'm still writing it here, and you'll understand that this set of parents is empty. Okay, so as an exercise, you can write this for naive Bayes if you want. It's going to be the same thing, only that the only parent that nodes have is the top node here, but the computation is exactly the same. Okay, so here is an example, or a couple of examples. So here is a representation of probability distribution, right? So I have 4 bits, so I need 16 numbers, or in fact 15 independent numbers. That's a probability distribution if I did not make a mistake, and the numbers here, the red numbers here, sum to 1, right? Here's another probability distribution. In fact, it's not yet a probability distribution, just a suggestion. I need to give you these numbers, and now it becomes a probability distribution. And here's another one. And again, I need to give you these numbers. Notice that these are different trees, and therefore different sets of numbers, right? The conditional probability tables are different, not only in terms of numbers, but the names of the conditional probability tables are different. And we can ask many questions about this. So one question we can ask, are these representations of the same distribution? What does this question mean? Or if you want to answer yes, or if you want to answer no, how would you go about answering this question? Yeah? Right, or saying it another way, so you said the table. If I compute the table from this tree, I get the same table. Or in general, whether the joint probability distribution is the same. Right? So this is, and remember this question because, in fact, this is your second question in the homework. I'm going to go back to this. Yeah? What I mean is that P of x1, x2, x3, x4 for tree 1 is the same as it is for tree 2 for all values that I instantiate for x1, x2, x3, x4. So I can either build a table, as was suggested, or if the table is too big, there are too many variables, I want to be able to show that these expressions are the same. So in general, I want to show that the expressions are the same. But that's the answer, or that's the way you're going to go about answering this question. Show that the joints are the same. You can ask other questions. You can ask, given a sample, which of these 3 distributions generated the sample? Right? That's another computational problem that you can ask, and we're going to answer. And you can also ask, or this is the specific question, right? So I'm just instantiating the second question. Here are 3 data points. This is my training data, just a little bit of training data. And I want to know which of these 3 is the target distribution, or which of these 3 is the most likely target distribution. And should be easy to compute today for you. So let's go over it and see what do we need to do. So first of all, let's look at the table and see what's the likelihood of this table generating this data set. What do you think? What? Suggestion for 0. Why 0? Because 1011 is a data point and cannot be generated by this probability distribution. Right? So that solves it. And in fact, here I'm just writing it a little bit more explicitly. First of all, writing what we need to do. We need to compute the likelihood, which basically means I'm using this tilde here just to indicate that it's really proportional to P of D given T, because I'm assuming that there is uniform distribution over the trees, and I'm assuming that because I'm going to do argmax, I don't care about the denominator. So I'm just multiplying the probability that the tree gives to each one of these data points. One of them is 0, as you noticed, and therefore this table does not generate this data. A little bit more interesting, so the probability of the data given this table is 0. A little bit more interesting is if we want to look at the trees. Now, what I have to do is basically I need to give you a concrete instantiations of these conditional probability tables. And here it is. So notice that I'm giving you half the tables, right? So the probability of whatever is needed being 1 given whatever is needed, and you know how to compute the second one. So now I can compute the probability of the data. So let's take, for example, this, 1, 0, 1, 1. What I need to do is I know that the probability of this event is P of x4. Because it's a tree, and this is the structure of the tree, it's the probability of x4 being whatever it is, times P of x1 given x4, times P of xt given x4, times P of x3 given x4, with the appropriate instantiations. So here x4 is 1, x1 and x4 are 1, so it's 1 and 1, x2 is 0, given x4 is 1, and x3 is 1, given x4 is 1. And I'm just reading these numbers from here. The only thing to notice is that P of x2 being 0, given x4 being 1, is not given here, but I know that it's 1 minus a third. So I put here somewhere. Where is it? Oh, so it's wrong, actually, what I've written here. Right, let's check. P of x1, x4 being 1 is a half. P of x1 being x4 being 1 is a half. That's true. P of x2 being 0 given x4 equal 1. This is wrong. Should be 2/3. I'm glad we found it. Okay, and P of x3 being 1, that's true. This is 5/6. Okay, so this should be actually 10/72 here. Let's correct. What? 10 over. It's good now? Okay. Okay. I hope the others are okay. You can check. Anyhow, now we get the product of all the 3 data points, and I get something like this. Okay. Same thing happens for the same tree, only different conditional probability tables. And hopefully the numbers here are pretty correct. Either way, at least the comparison is, here you have something like this, which is, I don't know, 30-something over 3 to the 6, and here you have 10 over 3 to the 7. So I thought the distribution 2 is the most likely distribution. Maybe with the change in the calculation, it's even more the most likely, because I increased it by 2. So we chose among 3 candidates, we were able to easily choose a 3, right? So it's clear what we've done? Okay, so the key thing is that this was an easy problem, right? So this was an easy problem in the sense that it's very similar to the problem we started with when we talked about maximum likelihood. In that case, I tossed a coin, and I told you there are 2 options for the coin. Either it's a fair coin, or it's a 0.7.3 bias coin. And once we observed 1 toss, and later on 100 tosses, The question was which one of these is the most likely. And all you had to do is you had to compute for these two coins what's the likelihood of observing this data and choose the largest one. Same thing here, right? So we observed some data. We had 3 candidates. For each one of the 3 candidates, we computed what's the likelihood of the data given this distribution, and we chose the largest one. Of course, this isn't the most interesting case, as it wasn't in the coin. In the coin, the interesting case was, I have no idea which coin it is. There are infinitely many possible biases. Find P. And we had to have calculus in order to be able to do it, right? So we had to write a function that represents the likelihood of P given the data and find the maximum value of this. We'll have to do something like this for trees, right? So we need to find a systematic way to search the family of all trees if we want to be able to find the most likely tree. Okay, so at least I want to make sure that we understand the problem here. The problem isn't as easy as the one I just solved. And this is going to be the problem every time, you know. So I'm just giving it for trees here. If you have your own family of probability distribution and you want to find a member in this family of distributions, that's really what you have to do. It's unlikely that you'll have a small set of distribution and you can compute everything. So you need to be able to deal with this parameterization. And in fact, the reason I'm giving it for trees is because the algorithm comes out to be interesting, simple and interesting. Maybe not as simple and not as interesting for other families. Okay, but so I want to get to this, and I want first to discuss for 2 minutes, again, what we are doing here. So we have 3 data points in this case. What's the target distribution, right? So that's the question we're asking. Why do we care about this, right? So in fact, we know that we cannot find the target distribution. Our goal is eventually is what? It again? Why do we want to come as close as possible? What is the eventual goal, really, at the end? Yeah? So clearly we're going to go through a target distribution. So this is what you suggested also. But why do we want the target distribution? I mean, it's not just because we like target distributions. We want to do something with it, right? Eventually, we want to make predictions, right? So the question for us is, when we want to make prediction, we care about generalization, right? So for example, given some data, the example is these 3 data points. Hopefully, you'll have more than 3 data points. I want to know what's the probability of 1, 1, 1, 1. I want to know what's the probability of a data point that I've never observed. Or I want to know what's the probability of the event x1 is 1, x2 is 1. I don't care about 3 and 4. Or the event x4 is 0. That's what we want to do. And the issue is that you could say, you know what? You have data, just compute explicitly from the data this probability. I could do it, right? So tell me, what's the probability of x4 being 0 from the data? 1/3, right? But that probably is meaningless. So the reason we want to find a representation of distribution is because we want to generalize. We want to say the data that we've seen, and the assumption that I'm making, if all I'm doing here is looking at x4 only and computing, 1 out of 3, assuming that the distribution is uniform over the sample, and that's it. There's nothing else, which is wrong, right? I need to make some assumptions on what is the distribution that generated the data so that I can generalize to points that I've never seen. I cannot just assume that that's it. That's all the data there is. And again, we are in the same situation we were at the beginning when we showed this table of 9 examples. or whatever it was, 7 examples, and I ask you which function generated it. The reason you wanted to know which function is because you want to be able to say something about the value of the function on other points that you've never observed. And the only way to do it is to make some assumptions on what's behind the scene here, right? What is generating it? Same thing here. So we have to make some assumptions in order to support generalization, and under these assumptions, I'm going to find this target distribution, and then I will be able to answer these queries. Okay, so I just don't want us to lose sight of the real goal, right? So the real goal is not to find a distribution. We have good reasons why we want to find a distribution. Questions on this? Okay, so now let's go and define the learning problem that we have. So we actually have 2 options. Here is one problem we can formulate. Given data, assumed to be sampled from a tree-dependent distribution, find the most probable tree representation of the distribution, right? That's kind of what we had in mind in the last few minutes when we talked about it. Someone told us the data was generated from the tree, find the most likely tree. Yeah. From a decision tree. Well, the way we talked about decision tree, it was a classifier, right? So there was one variable that we cared about, right? And here, it's a representation of distribution. The fact that there are trees is a little bit misleading here, right? So they're just data structures, right? But they are data structures that are doing different things, being evaluated in different ways, right? So we care about tree now as a distribution, and this could be one question. Could be another question, right? So given data, no one told me how the data was generated, whether it was generated from a tree distribution or a more general distribution. And still, I want to find the tree representation that best approximates the distribution. Notice that these are 2 different questions, right? So in 2, I actually make no assumptions on the data. Here's data. No idea where it came from. In 1, I do make an assumption where it comes from. What does this remind you if we go back a month and a half? Hopefully you remember. We talked about, when we talked about PEC learning, for example, right? We talked about, here is a function that generates the data, and we want to learn it. We're going to use hypothesis class H to learn it. And the hypothesis class, we said, has to be as large as the class of functions that generated the data. Otherwise, we'll never be able to be consistent. That was our first game. And under this game, we showed that we can be consistent, right? We have expectation to get empirical error 0 because H could express the target function. And then we said, let's relax this and deal with the more general case where I have no idea which function generated the data. Still, I have to define how I'm going to learn it. I'm going to learn it using functions from H. But it could be that H is not as expressive as needed, and therefore the empirical error will be non-zero. Still, I want to minimize the empirical error. So this is the analogous situation, right? This is a strong assumption, potentially a strong assumption. Here, there's no assumption. In both cases, I want to learn into decision trees, and the reason I want, into probabilistic decisions, this is bad priming, into probabilistic trees, and the reason is that that's what I want, that's what I know how to do. Okay? So here is the game that we're playing here. So think about this. This is the space of all tree distributions. And in this space, there is one, this is question 1. In this space, there is one distribution that has generated the data we are observing. and I want to find it, or I want to find something that is most probable given the sample that I've seen, this distribution. Question 2 says, let's consider the space of all distributions, much larger. Now the target distribution could be here, right? Still, my hypothesis is going to be this black circle. So I'm going to try to find something here that is the closest to the distribution that generated the data. So that's the game we're playing now. And again, the reason we're playing this game is because we can. Because, as you'll see, there is a nice algorithm that can do this, irrespective of where the data is coming from. Okay, but again, I want the most important thing is for you to understand what we're doing. I mean, how do we formulate these problems? Okay, so this is what we're doing, right? So the simple-minded algorithm is going to be this. For each tree, compute the likelihood and find the maximum, right? And what we're going to do in the next few minutes is show that there is a nice algorithm that does this without actually writing down all the trees, which we cannot do. Okay, so we need a few tools for that. So the first thing, because I'm looking for, yeah. Yeah. Well, so the issue with probabilistic representation is, first of all, we never check for empirical error, although we could. But now our metric is a little bit different. Our metric is not measure errors because there's no notion of error, right? All we do, I mean, before we had a variable that was our target, and we wanted to know how well do we predict this variable given the function that we learn. Now we don't have a variable, right? So we have essentially a representation of distribution. So here is the data that we've seen, and here is a representation of distribution that presumably has generated this data. I don't have a notion of error. I need to have another notion of how do I know that this is good. And in fact, we already gave this notion. We said it's maximum likelihood. We're going to look at what is the most likely tree to have generated this data. In both cases, it's going to be the closest possible tree. The only issue is that perhaps the algorithm needs an assumption. You could imagine an algorithm that needs to know that the data was generated one way or another. And here you will see that we're not making any assumption on what has generated the data. In this sense, we are in problem 2. Right? The algorithm is going to make no assumptions. But we do need the notion of a distance, which is the first thing I'm going to introduce. So there is a probability distribution that presumably generated the data. And there is a probability distribution that we are going to entertain. And I need a notion of distance between them that I want to minimize. And that's the first technical notion that I'm going to introduce. So first of all, before I introduce this notion, it should be clear to you that there's nothing scary about distance between probability distribution. Probability distribution are just functions. And in this case, we're talking about discrete probability distribution. Okay, so I have probability distribution 1 over, let's say the space 1 to 100, or the space of the Boolean cube of size 32, which means it assigns a number to each one of the 32 elements, numbers that sum to 1, and then you have another function that does the same thing. Very easy to define distance between them. For example, you can define an L2 distance. For every data point, look at what P1 says about this data point and what P2 says about this data point, and take absolute value of this and sum them over the data point. Or take, the square of this or something like this. Very easy to define distances between functions, right, if you think about it. And there's nothing different And therefore, there are many, many ways to define distances between probability distributions. I'm going to define one specific one. And the reason is that this one specific one has some nice properties that we're going to exploit in this algorithm. It turns out that almost all sensible ways you define probability distances between probability distribution behave about the same in the sense that they all grow together and go down together. I'm going to define this distance. So the distance between two probability distribution P and T is going to be the sum over all data points. These are discrete probability distributions that I'm assuming here. P of x log P of x over T of x. Right? So it's called KL divergence, and it's non-symmetric, right? You can see that really it measures how much P differs from T. It's non-negative, easy to see. Also, easy to see that the KL divergence of P comma T is 0, if and only if P and T are identical. And that's enough. Okay, so now we need to be able to, the second technical thing, yeah. Log is, let's see, why is it non-negative? It again?
This is cross entropy.
Right, so it's P log P minus P log T. Actually don't see it immediately now, but it's true. I have to think about it. For someone sees an argument for why this is always non-negative. Yeah? Okay. So we need a pencil to think a little bit about it, but it is non-negative. Yeah? Go ahead. Is 1. Yeah, but immediately, how does this lead to that? Okay, so let's take it as an exercise. We'll have to write it down and get it. It should be very simple. It's just 1 or 2 lines. Okay. The second technical thing that we need to do is we want to be able somehow to rank dependencies. When we have a probabilistic tree, we're going to have edges between x and y. And we want to be able to know when do we want to keep edges and when we don't. And there are many ways to measure dependencies between two variables. And given that we measure the distance between the distribution using KL divergence, the corresponding measure of dependence is going to be the mutual information between x and y, which is defined this way. So the mutual information between two random variables x, y is going to be sum over all x, y, p of x, y, log p x, y, p x, p y. So essentially, if you can think about it as the expectation over P of this ratio. Given data, we'll be able to estimate this quantity, the mutual information between x and y. Okay, so now we can start learning. So the algorithm is going to be given m independence measurements from some distribution P. And what I'm describing now is essentially pseudocode for the algorithm. First of all, for each variable, we're going to estimate P of x. Notice that I need it even for the mutual information, right? I need to know for each pair xy, P of xy, and I need to know P of x for each variable. So these are n variables, n numbers. For each pair of variables, I need to estimate P of x, y. And notice that already here I have order of n square numbers. Right? So again, this is important to notice because if you think about naive Bayes, the number of parameters that you had to estimate was linear in the number of variables. Here it's quadratic. So if you have a million variables, you probably cannot learn trees over them. And this is one of the key difficulties of learning representation of distributions over a large number of variables. It's actually the space. Right? You really have to represent a lot of stuff. But if you have 1,000 variables, that's not a problem today. Okay, for each pair of variables, compute the mutual information. We know how to do this. Right? So now that I have P of x and P of xy, I know how to compute the mutual information. And I'm going to build a complete undirected graph with all the variables as vertices. Okay? Simple so far. Now the algorithm really starts. I'm placing on the edge xy the mutual information as the weight. And build the maximum weighted spanning tree over it. So now I'm actually moving from the clique over all nodes into a tree over the nodes. And just to remind you, how do I build a maximum weighted spanning tree? It's a very simple algorithm that you know. Sort the weights, and in a greedy fashion, start with the largest one, add the next largest one, as long as you don't create a loop. If there is a loop, discard this weight, move on to the next one, and basically keep on going. Very easy to see that you're going to get a tree. You're going to touch all vertices. So it's a spanning tree. And it's also not hard to see that it's the maximum weighted spanning tree. So again, this is an algorithm that you've all seen, simple algorithm. And now we have a tree. Now we have to make it a probabilistic tree. And in order to probabilistic tree, first of all, you have to make it undirected, to make it directed. The way we're going to do it is we're going to choose a root variable and set the direction of all the edges away from it. So if you think about it, there are many, many ways where you can take an undirected tree and make it a directed tree. I chose one. Basically, randomly, I chose a variable and set all the directions away from it. Okay? And now, to complete making it a probabilistic tree, I'm placing, I need to complete the conditional probability tables, which are the conditional probabilities. And I'm placing the corresponding conditional probabilities on the edges. Okay? So that's an algorithm. Yeah? So this is just pre-processing, right? I just computed some things. I built a graph. I placed some numbers over the graphs. Now I have weights over the edges. I'm using these edges, these numbers on the edges, as a way to prune some of the edges and generate a tree. Specifically, the way it's done is choosing a maximum spanning tree with these information gains as the weights. Okay, so I started with a graph, I made it a tree. It's an undirected tree. Now I'm making it a directed tree. How do I do it? I choose a node, and I say, okay, you're going to be the root. Let's direct everything away from you. I got a directed tree. Maybe you're not happy with the way I did it, but first of all, let's make sure that what I do is giving me what I want. It gives me a directed tree. That you agree. Once I have a directed tree, I have to make it a probabilistic tree. and I have to place conditional probability tables, I know exactly which conditional probability tables I need because I look at the directed tree. I have names for the nodes, and I say, okay, you have an arrow from A to B, compute P of B given A, and so on. Yeah. Just over there.
The versions are represented by, are these variables supposed to be only?
Variables are just variables, x1, x2, x3, and so on. The mutual information are just numbers. Every two variables have a number that relates them, and this number is the mutual information. How do I compute the mutual information? I look at all the values that x and y can take and use this formula which I showed before. What is the... I'm not sure I understand the question. Let's go back, for example, to this definition. Right? So x and y are two of the variables. Right? I have a vocabulary of n variables here. Right? Let's assume that x can take two values, 0, 1. Y can take two values, 0, 1. So basically what I'm doing here is I'm summing over, I should have written here x in 0, 1, y in 0, 1, these quantities. Okay, so basically I'm summing over four numbers here. Right, and I know what is the probability that p is 0 and x is 0 and x is 1 because I counted, and I know the joint because I counted, and everything is fine. Just sum of four numbers. In fact, I'm going to give an example a little bit later, or at least show an example. Yeah. Okay, that's actually a good question. So now that we have an algorithm, you can ask, why is this the right tree? And in fact, there are three questions that you can ask. So first, you can ask, how do you place the conditional probabilities on the edges? Right? So I have a tree, T. I had data. The data presumably came from probability distribution P. What I'm going to do in order to put the conditional probabilities on T is take statistics on the data that came from P. I need to justify that this is the right thing to do, and I'm kind of going to justify. This is the hardest step, in fact, because it requires some knowing something. Two, I need to justify why was it right to place I of x, y on the weights. You could have measured other things to measure the dependence of x and y, and I chose to do mutual information. I need to justify that. And three, I need to justify the seemingly random behavior here, where out of all n nodes, I chose one, and I said I'm going to direct away everything from it. Okay? So once I show all these, then I answer your question, because I showed that this is the best tree in the sense that I mean best. So let's just go over this. Question there. I don't have a tree yet. Right? I don't have a tree. What I have is a bunch of nodes, and part of the algorithm, I'm constructing the tree. So it's not like an EM algorithm, right? It's really a direct computation. It's a direct computation that takes, 7 steps, but really it's just direct computation, right? Okay, so let's just justify it. And actually for 3 is your homework problem, but I'm going to give you a hint. And 2 and 1, I'm going to almost completely prove just with a little bit of leftovers. But it turns out that it's essentially algebraic manipulation of the probability distribution. So the first thing I want to justify is, why is it okay to place the corresponding conditional probabilities on the edges, or how do we want to place the corresponding conditional probabilities on the edges? So here is the problem. I'm given a tree. It defines the probability distribution T, and the way I'm doing this is I'm forcing the conditional probabilities along the edges of D to be those statistics taken from P, the data that I got, right? So, let's just justify it. So let T be the tree-dependent distribution. So T of X is this. And I'm going to measure the distance between T and P using this scale divergence, which I'm going to rewrite here. So I can write the scale divergence between P and T as this. Just opening it is P log P minus P of X log T of X. This, if you recall, is just the P entropy, right? The entropy according to probability distribution P. And I will not need this anymore. It will not matter because it's fixed, really. It's something that depends on P. And here I can write this this way. Let me just copy. Okay, this is just this usual slight abuse of notations at the root. I'm just assuming that it has parents. And basically, I want to know how to define this so as to maximize this component. Okay, so this is just, I actually already did this before. So you can think about this as expectation according to P. Right? So I have sum over all data points, P of X, something. This is just the definition of the tree. I'm writing this as an expectation of this sum. And I'm taking now the sum out of the expectation, replacing the sum with the expectation. So I'm getting this. From the definition of expectation, I can now write, okay, so this is sum over all possible values of xi, comma, the parent of xi, the probability times whatever I have here. And now basically I'm splitting this. So I can write P of xi, comma, parent of xi as P of xi given the parent times P of xi. Now the parent does not depend on this. This is just another variable, so I can split the sum over xi, comma, parent of xi to sum over parent of xi, sum over xi, which I'm writing here this way. So this is the simplest way I can write this. And now basically what you see here that I have P of this conditional probability, log T of this conditional probability. And this is where I'm relying on the fact that this is going to take its maximal value when T is equal to P, which is something you'll have to believe here. So basically, once you believe this step, we can summarize, we'll summarize later, I guess, and basically say, because I want to maximize this guy, and I'm saying that this expression is maximized when I'm setting T to be P, the right thing to do on the edges is to compute the conditional probability relative to the data that I have. This is the conditional probability, right? For every edge, compute P of xi given the parent. For every two edges, compute P of xi, P of one of them given the second one. 2 is actually easier. So I want to know why is it that I used I of xi and not some other way to compute dependence between x and y. And we've just written this before. If you go back, you'll see that this is the expression that we had before. Now, let's think about what is P of xi given pi of xi. I can just write it as P of xi comma pi of xi divided by P of pi of xi. So this part is exactly this. And I'm also dividing again by P of xi, but also multiplying by P of xi. I've written it as a log of the sum. But basically, this is what I had on the left. Divide by P of xi, multiply by P of xi. So going back to all this expression that I need to do, I need to get it, I'm taking this and just multiplying it by P of xi, pi of xi on both sides. So I have it here, and I'm multiplying this expression by this. All I did is just multiplying by something. And I claim that now this gives me a representation of this way. So I had h of x, I just copied it. I have sum 1 to n. Notice what do I have here? This first expression is essentially the mutual information between x and its parents, between every two variables. And what I have here is, notice that I had this sum. I'm summing it over xi and pi of xi. I'm splitting this sum. When I'm summing this over the sum of xi, I'm getting just P of xi. And therefore, what I got here is sum 1 over n, sum over x, P of xi, log of P of xi. So this was just algebra and playing with conditional probabilities. And now the key observation is that if I want to maximize this, I notice that this has nothing to do with the tree, just a property of the originating distribution. And also this has nothing to do with the tree structure. The only thing that really matters here is this component. So if I want to maximize this, I need to maximize the information gain between every two nodes. So basically, maximizing minimizing the distance, this is in a minus sign here, is achieved by maximizing the sum of the mutual informations. So basically, we justify the second step, which is why did we play with I of xi? Why did we place this on the edges? And the final step, okay, this is just saying the same thing. The minimization problem is solved without any need to consider all the possible trees. So I basically showed that this is the crucial step here, right? Once I place these numbers on the edges and minimize, I got what I want. The last step that I need to justify is the reordering of the nodes. Transform the resulting undirected tree to directed tree. And as I said, I'm just doing it by choosing a root and directing everything away from it. So let me just make this a little bit clearer. Let's go to this picture that we had before. Yes, this one. Okay, so here's a tree. Imagine that it's undirected. Okay, so don't look at the arrows here. So you have a tree. This is the output of the spanning tree algorithm, right? Now, notice that I have a lot of options. I can choose x4 and then generate x4 to x1, x4 to x2, x4 to x3. This is one tree. I could also have chosen x2 to be the root. And then I will have an edge leading from x2 to x4, and then edge leading from x4 to x1. This will go up there, and leading from x4 to x3. It will look differently, right? And what I'm arguing here is that it doesn't matter. You can choose x4 and get this tree. You can choose x2 and direct everything away from it. You're going to get the same probability distribution. Okay? And this is really what you'll have to do. And we already talked about what does it mean to get the same probability distribution. So in your problem set, the second part, you'll just have to write this down. My suggestion is to take one example on this tree. In fact, I'm going to give you here an example, but I will not work it out. You can work it out. And just convince yourself that this is true, and then figure out how to write it down explicitly. Okay, so basically this is the summary. Just as a historical note, this algorithm is called the Chow-Lu algorithm. Was actually invented not in the context of learning, but rather in the context of compression of data. They started with a lot of data. They wanted to compress it, so they compressed it into a tree that had this property, and was adapted by Judea Pearl to Bayesian networks in his book on Bayesian network that was written in the late 80s, and since then was invented several other times. But okay, here is an example. I don't want to work out this example, but you can try it. It's basically 4 data points, four variables, starting with the same data point that before, and you can just do the computation. The numbers here, I write here approximate, because I actually didn't take the log when I computed the IAB, because I did it, wanted it to simplify the computation. You can go over it, and then you can generate the tree, press the probability, and order it by choosing several roots. You have 4 options, and see that you get the same probability distribution. Okay, so basically, I want to finish this here. So I think it's a very nice algorithm, very nice because it learns actually a very complicated thing using a very simple algorithm. We can't do as simple things for general representation of distribution. The nice thing is that for trees we can do it. So we have a simple algorithm. So there's a lot of still open problems in learning probabilistic representation. For example, very little is known on how many examples are needed in order for it to converge. And there's even a notion, you can think a little bit about what exactly do you mean when you say converge. And I just want to finish it by reminding you why are we doing this, right? We're doing it because we want to be able to generalize. In order to generalize, we need to invent some structure, invent some dependencies or independencies, assumptions. Otherwise, we just have to answer the query directly from the data, and we know that we don't want to do this. Okay, questions? Yeah.
So what's the difference between undirect tree and a
Direct and undirected? One of them has arrows that go from A to B, and the other one doesn't. So you're asking a graph theoretic question, or you're asking about?
Yes, because you mentioned that whatever you choose from, whatever nodes you choose from a tree, and then consider it as a exact probability distribution from the tree, right?
Right. So first of all, we did not define a probability distribution over undirected graph. There is a notion like this, but we defined only over directed graphs.
Okay, yeah, that's my question. So what is an undirected graph?
Undirected graph is a graph that has a collection of nodes and edges between them, but no direction on the edges.
Okay.
Now, we define probability distributions over directed graph only, right? So the direction gave us the notion of what are the conditional probability tables that we had, right? So we don't know what does it mean to be a probability distribution over undirected graph. There is a notion like this, but we just didn't talk about it. So for our algorithm, because we want to get directed graph, we need to take the outcome of the spanning tree algorithm and add directions to the edges. All I'm saying is there are many ways to add directions to the edges, right? Here is one of them, and my argument, and the one I chose was choose a root, choose a node, make it a root, and direct everything away from it. Now, if you have n variables, you have n ways of doing it. Right? I can choose any of them as a root. What you will prove in the homework is that in all cases, you will get exactly the same probability distribution. Okay? Yeah. Yeah, so this actually, it's a good question. This actually shows that interpreting Bayes net as causal net is actually wrong, because you can get exactly the same distribution over the same variables by changing the directions of the edges, which basically means that causality is not the right attribute. It's basically independence assumptions. I mean, the fact that you see sometimes in the literature, and in fact, I also said that, you can call it causal relations, it's not true. It's really dependencies and independencies that we are encoding. So I'm not going to talk about causality. It's too complicated. And it's a very active research area. So there's actually a really nice book that came out a couple of years ago on causality. And there's a lot of research now on causality. Judea Pearl has a book on causality that is kind of laying out the beginning of theory for this. I'm not going to talk about it, but your question actually is a good question because it serves to indicate that I cannot interpret the graphical structure as causality, because I can get exactly the same thing by changing the directionality. But if we want to say more, there's a lot more to say about it. Okay, I want to stop here because we have to have the annual ceremony of doing evaluations. So I assume several of you have done it before. Some of you have never done it. So, okay, so first of all, I'm going to spread this around. Don't start yet because I have to read something. So I'm sending up. You'll probably have some change. So this is the most important part of the class, so don't leave now. Okay, so first of all, I need a volunteer to put this in a mailbox. Volunteer, okay. So just make sure I'm putting everything back to the envelope, collect everything, put it in the envelope, and put it in a campus mailbox. If you don't find a campus mailbox, you can give it to my assistant. She'll find it. Oh, also, it has to be with pencils. Sorry, I forgot the important pencils. So I'm sending pencils up also. Yep. And if possible, when you put it back, get the pencils also. Okay, when you can give the pencils back to my assistants. Okay, I have to read you the instructions. These are the rules. Okay, so the purpose of this, just bear with me one more minute. The purpose of this is to provide me with evaluative information based on your perception of the course. The results will not be sent to me until after final grades are reported. And without reading it, I really appreciate if you do it. What I'd like you to make sure that you do is, at the top of the form, there are two questions, 1 and 2, that are the most important questions. So make sure that you respond to 1 and 2. On the back, there are questions that you can write text, and I really appreciate if you write something there, because I read it. And other than that, you don't need to complete the demographic information in item 5. Again, make sure that 1 and 2 are completed. And I think that's it. And other than that, have a happy Thanksgiving break. And I'll see you after the break. So I'm leaving it here. Just put everything back in the envelope and put it there. Thanks. Pencils are coming. I'm hoping. Where are the pencils? Okay. You have to do it with a pencil. They don't like non-pencil things. You can do it in the academic office, yeah.